Have you ever heard of something called a time crystal? No, it's not some futuristic artifact from a sci-fi movie. It's real, and it's one of the most fascinating discoveries in modern physics. In today's video, we're going to explore what time crystals are, how they defy the usual laws of physics, and why scientists are so excited about them. So, buckle up because this is going to be a journey into the cutting edge of science. Before we explore time crystals, it's important to first understand regular crystals. Crystals such as quartz in your watch or the salt on your table are remarkable because of their highly ordered atomic structure. In physics, we describe this order as exhibiting translational symmetry. This means that if you shift the crystal by a specific distance along certain directions, called the lattice vectors, the arrangement of atoms appears identical. This periodic repetition in space defines the crystal lattice and gives crystals their distinct physical properties such as sharp edges, well-defined cleavage planes, and characteristic mechanical and optical properties. In regular crystals, this symmetry and periodicity exist in space. Time crystals, however, exhibit periodicity and symmetry breaking in time rather than space, creating a fundamentally new state of matter. Understanding this requires a shift in perspective. Instead of static spatial order, we examine systems that exhibit repetitive dynamic behavior in time while remaining energetically stable. This is where things get truly fascinating. In physics, most systems obey something called time translation symmetry, which means that the laws of physics remain the same regardless of when you observe the system. But here's the thing. Time crystals break this rule in a very special way. Imagine a system that has a repetitive pattern, not just in space, but in time. Sounds strange, right? But this is exactly what time crystals do. A time crystal is a phase of matter where the system exhibits a repeating pattern in time, oscillating between different states without consuming energy. Unlike a pendulum that requires energy to keep swinging, a time crystal maintains its periodic motion without any external input. This perpetual oscillation occurs because the system's components interact in a way that leads to spontaneous time translation symmetry breaking, resulting in a stable yet ever-changing structure. Creating a time crystal requires a system to be driven periodically, keeping it out of equilibrium. For instance, in 2021, researchers used Google's quantum computer Sycamore to engineer a time crystal. They applied a sequence of quantum operations to a set of qubits, causing the system to oscillate between states in a stable, repeating cycle without absorbing net energy from the driving force. This experiment demonstrated the feasibility of realizing time crystals in controlled quantum systems.